Testing, testing. Okay. Hello, everyone. We're going to cover PowerPoint number 5 or chapter 7, which is hypothesis testing for t-test. And there are 3 different types of t-tests, which you're going to go over one of them shortly. Just 1 second so I can pull up the PowerPoint. Okay, here it is. PowerPoint number 5, chapter 7. It's about hypothesis testing applied to means. And for that, we're going to cover 3 different types of t-tests. Today, we only go over the first one. And keep in mind that this is all about research. What type of research you're going to use and what type of test statistics to use. Before this, we talked about z-score. The difference between z-score and t-test is the fact that for the t-test, we no longer have access to population means or standard deviations. So for that, we have to estimate that by using a sample. I explain that as we move forward. So there are 3 different types of t-tests for different reasons. Single sample t-test, as the name suggests, you take one sample from one population. This is very popular in college and universities, and it's called student t-test or one sample t-test. Keep in mind, one sample from one population. Next time, we're going to go over related sample t-test or repeated measures. Keep in mind that they have different names. So let's say let's say you never heard of a paired sample t-test, it's the same thing. It goes by different name, as you can see. So for this, which we're not going to cover today, number 2, you have one sample from one population, but just like the name suggests, paired or repeated, you repeat the procedure with the same population, like before and after, pre-test, post-test. And finally, the third one, which is called independent sample t-test or 2 independent. For this one, you have to have 2 samples from 2 different populations. This means that let's say if you're comparing FIU students with AU students. So you have two populations, FIU and AU. And then you take a sample from each population. So you have two samples. That's what it's called, two independent sample t-tests, or for short, we'll call it independent sample t-test. And keep in mind, once we finish this, we start ANOVA, analysis of variance. And analysis of variance is the follow-up on t-test. We will have independent sample design, one-way ANOVA, and repeated measure design, one-way ANOVA. But for now, let's just focus on that highlighted area, which is a single sample or one sample t-test. Every test statistic that we're going to cover, or we covered, or we will continue to cover, like all these t-tests, ANOVA, ANCOVA, MANOVA, MANCOVA, correlation, regressions, and beyond, they all are under the umbrella of parametric tests. When we use these tests, we have to go by certain assumptions. And here they are on screen, assumption of parametric test or assumption of the t-test. So this means you're only allowed to use these tests when you meet these assumptions. Otherwise, you're not allowed to use them. So for that, there are another set of statistics which we call non-parametric t-tests or non-parametric tests in general, non-parametric tests. If we can't meet this assignment, that it doesn't mean you can't conduct research. For example, look at the third one. You have to have your sample size should be at least 30. So what if you work in a psychiatric hospital, let's say, and you have only 25 patients in, let's say, schizophrenics ward? Does this mean that you cannot conduct research? No. You cannot use the t-test, but in here, I mean, when you don't meet that qualification. But you need to know what is the non-parametric test equal to the test that you are using, whether it's t-test, any kind of t-test, or ANOVA, or anything at all. So we will talk about every time from this point on, and every test that we cover, which is parametric test, we will go over the non-parametric test. We're not going to manually calculate the non-parametric test. We will use SPSS for non-parametric tests, but we do go over the manual calculation of parametric tests. So again, the rule of thumb is that at least keep in mind this is minimum 30 participants for each variable that you're using in your research or for each group. If you can't meet that assumption, then you cannot use the t-test in this case. The second one is the population sample must be normal. For t-test, we use the same distribution as we did for the z-score, normal distribution or bell-shaped, with the mean of 0 and a standard deviation of 1. It goes to right, positive, 1, 2, 3, left, negative, 1, negative 2, negative 3. So the distribution is the same as z. But in terms of being, again, normal, we wanted to make sure the population that we use for our sample, to take sample from, participant people in that population share similar socioeconomical status. And number one is the values in the sample must consist of independent observation. We already explained that what independent observation is, but that's for probability. It means that, for example, if you have a jar of 15 marbles, 5 green, 5 red, 5 yellows, if I take, let's say, the probability for me to take one red marble will be 5 over 15. 5, which is the red ones, divided by total number, which is 15. But for the next person, let's say somebody wanted to, what's the probability for the next person to pull a green one? It'll be same thing, 5 or 15. This means that if I stick my hand in that jar and take a one red marble, it means that after I'm finished, I put it back. Well, same principle applied for research. If I say that Albizio have 1,000 students, then my sample will consist of 200. It doesn't mean there's 800 participants left for the next researcher to conduct research. Once I'm done with my participants, they go back in the population, and the population will still stay the same, 1,000, except that is for that semester. It says there's an exception if we use, for example, right here, somewhere it says, if we use a longitudinal study, like year, 2 years, 3 years, then the population, the number of participants number of students enrolled in university will changes. That's understand. It goes up and down. But for the semester, we assume like we have 1,000 students. Okay. So again, you can take unlimited samples from a population, even though there are 1,000, but I can take a sample of 200, the next person 300, the next person 500, 600. They all go back into the population. This is the meaning of of what I just described. This is the meaning of the value in the sample must consist of independent observation. And then again, we talked about the normal, must be normal. And then the reason for that, if you have less than 30 participants in your research per variable or groups, then assuming this is a normal distribution or bell shape, if it's less than 30, then the shape, as you can see, is not going to stay normal. It's going to become either pointed or flat, because because sample size is related to df, degrees of freedom, df. The formula for df, we said that is n minus 1. You take away 1 from sample, especially if you have one sample and consists of, let's say, 30 participants. So your df is 30 minus 1, 29. If you have 1,000 participants, your df is 999. Let's just take away 1 because we have one sample. So on the same token, if your sample size is 21, then your df is 20. So an effect. What is DF? DF is degrees of freedom. The freedom of right there under under that the curve will be scores, like a score from the participants. So somebody's going to have 100, somebody has 50, somebody's 80, 70. How these scores move from low to high, degrees or dispersion of the scores under this curve is called degrees of freedom. It's related to sample size. So the more, the better. Why? Because it's it's better representative. Your sample will be better representative of population. And think about it. And once again, back to Albizio, if somebody conduct the research with 50 participants, and then another person conduct the research at Albizio with 500 participants, which one has more power? Power means power to reject a no, power to say with certainty that it is so. There are correlations or there is effect. The more sample size, the more power you have to reject a no. So with that in mind, we said that if we cannot meet the parametric test, the assumption of parametric test, we need to switch to non-parametric test equal to that t-test or to that test statistics. As you can see, today we're going to go over one sample t-test with single or one sample t-test, and if we can't meet the assumption, let's say we don't have enough sample size, then we cannot use the t-test. We have to use one sample sign rank test, which in short is called sign test. Just sign test. Highlight it. Just sign test. Next time we're going to go over pair sample t-test, and again, if we can't meet the assumption of that t-test, then we need to use Wilcoxon test. And then again, independent measure design t-test, if we can't meet that assumption of that t-test, then we got to use Mann-Whitney t-test or test, Mann-Whitney test. So we talk about those two at the bottom. So tonight we're going to do a research example, and even though we're not going to use 30 or more participants because we have to start from scratch. So we only use like 9 or 10 to simplify the calculation. But we're going to use the test statistics single or one sample t-test. Even though it's not appropriate to do such tests with such low numbers, but point here is to show you how calculation is done. It doesn't matter 9 or 10 or 5,000, but if you put too many numbers, you lose the connectivity. Like the point here is to understand the calculation. Again, the fewer the numbers, it's easier to show you how it's done as opposed to make error in the calculation. And you're going to see that we're going to use SPSS to conduct non-parametric tests, which is sign test for single or one sample t-test. And that would be more appropriate if we have only 9 participants. But again, the goal here is to show you both, and you will see the differences in here. So what kind of research we can conduct with one sample t-test? The one sample t-test is a statistical procedure used to determine whether a sample of observation could have been generated by a process with a specific mean. We only need a number, just one number, to compare our sample with. Keep in mind that in z-score, we compare our sample mean, let's say mean of IQ test of our sample, with the population mean, which is known. And we know that the mean for IQ, the population IQ, is 100. We compare it with that. But for t-test, why do we use t-test in the first place? Because we don't know the mean for the population. Therefore, we have to estimate the mean for the population by using estimated standard error, by using our sample, standard deviation, and variance, either or. And you will understand more clearly as I move forward. So you got to compare it with something. It's not the population really. It's like, for example, you say the average, okay, this one says, name these hypotheses. Are these one or two tail tests? Back to refresh your memory about hypothesis testing, we said that if we are saying something is greater or less, it's one tail hypothesis, which is called directional hypothesis. But if we're not saying greater or less, then it's two-tail hypothesis or non-directional. This is something you need to remember, and especially for your comprehensive exam question. So if you say the average height of graduate student at AU is 5.5, you're not saying that is greater than, is more than 5.5, and you're not saying is less than 5.5. You're just saying the average height of graduate student at AU is 5.5, no more, no less. That is two-tailed test, or two-way, or non-directional hypothesis. You're not direct, you're not saying they are taller or shorter, but it's saying that those two at the bottom, example 2 and 3, yes, you are indicating they are taller or shorter. So those are one-way hypotheses. And here's the answers. Suppose you are, okay, so this is again, we're focusing on one sample t-test, which you need one sample from one population. Suppose you're interested in determining whether an assembly line produces laptop computers that weigh 2 pounds. So research question is, are these laptops 2 pounds? That's two-tailed hypothesis. You're not saying they seem to weigh heavier than 2 pounds, or they feel lighter You just want to make sure. You want to conduct research to find out. To test this hypothesis, you could randomly select a sample of laptop computers. So keep in mind that your participants not always human. Sometimes you work with product, and you're going to see in a second another one. From assembly line, measure their weights and compare the sample with a value of 2. So the number that you need to have is that 2. What do we compare? Because we don't know. We don't know what's the average weight of a laptop. It's not like IQ that we know the average IQ is 100. With that, you use t-test or some psychological tests, Wisconsin card sorting, GRE, ACT, SAT. These are all we use Z-score because we know the average mean is they are standardized tests. But for t-test, we don't know. We don't know what the to average laptop should weigh. But again, this company they say it's 2 pounds. Okay. So even though nowadays they feel lighter than that. So you take a sample of laptop, you weigh every one of them, and you find the average, whatever the difference is. Whether it's 1.5 or 2.6. So there'll be a difference that between your sample size, the mean for your sample size, and what you comparing it with. But the question is, but that's not the end of the story. That's just the beginning of the story. The question difference, is that difference between, or the effect size, between your sample size, the weight of your laptops, and that 2 pounds, is that difference significant, or does it have a statistical significance? We cannot answer that question by just looking at it and guessing, except to follow our hypothesis testing. Step one, and it's always the same. That's why you need to learn that ASAP. Step one, Noel always says, uh, it's the same, no difference, nada, no difference, zaps, zilch, zero. That's what H0, H naught is a symbol for no. If you say more, Noel says no difference or less. If you say less, Noel says no difference or more. Again, if you say there's no difference, Noel says, if you say there are differences because we think there are differences. Noel always says no difference. No difference, that means if this is 2 pounds, if you want to have a sample of 200 laptops, right? The weight, the average weight, it's going to be about 2. 2 minus 2 is 0. The difference between 2 and 2 is 0. No difference. So again, we have to prove that. We have to use a statistical procedure to prove or disprove. So step one, Noel always says no difference. We as the researcher, or H1 or HA, always says we think there are differences, more or less. Step two, we need to find our critical value for the t-test. We did the same thing with the z-score. Now we need to find what the critical value for the t by using the critical value tables in back of your book. Step three, calculate the t. The t calculation is pretty much just like z calculation. And the difference is, instead of sigma, which is a standard deviation for the population, we use S, which is a standard deviation for the sample. We no longer have access to a standard deviation for the population, which is, again, for IQ, is 15. For the mean is 100. But we don't know what the standard deviation for laptop is, or what the average laptop should be. Therefore, we use t-test. That's the difference between the t and the z. So this is pretty much what I just mentioned. You can read it. And there's another example, pretty much the same. Now, again, I'm sure many times you experience that you get a big, large bag of Dorito, and then when you poke it and you open it, you realize, oh, it's all air. And if it says 16 ounce, that's like a pound. But you realize that I don't think this is a pound because it was all air. So conduct research. You take a sample of these Doritos, and again, the number that you're going to compare with is 16 ounces. So you weight every one of them, whatever, 50, 100, 200, the more the better. Find out the average weight for all your samples, which are bag of Doritos. Compare that. Let's say it's let's say 14 ounces. The mean will be for your sample 14 ounces. But you're comparing it with what it says, which is 16 ounces. There's 2 ounce difference. But again, it depends how you state your hypothesis. If you say less, okay, or more, or they weigh the difference. There's some difference about this bag of Doritos. I'm not sure if they 16 ounce or more or less. That's non-directional hypothesis. So think about the way you address your hypothesis. You state your hypothesis. And then same thing, you follow that. You have M is the symbol for your mean or average weights for the Doritos, and mu will be the 2. I mean, it will be the 16 here, 16 ounce, the number that you need. For the previous example, laptop, mu will be 2 pounds, and you place it in the computer or you use it in calculation. Because we don't know the average, what's the average weight of Doritos? It says 16 ounce, but are they? Or the average weight for the laptop, they said is 2 pounds, but is it? Are they uh, 2 pounds? We conduct research the product to see if it is so or it is not. If the difference is very, very small, then we have to retain the null. That means it's not significant difference. But if it's difference, that number is going to show that, yes, there are significant differences. So we reject the null. Null says no differences. Okay, let's do a research example. All the formula that you need for tonight is this. As you can see, I compare the t-test formula with the z-score formula. On the left column, you see that on top left, it says z-score for single sample, and then, which we're done with that long time ago. But at the bottom, the second red dot, it says z-score for the research, and I arrow to the right as to show you that the t-test formula is pretty much just like z-score. For example, you can see On the left says Z is M minus mu divided by a standard error, or sigma M. For T, again, M minus mu. But the difference is M is in both means the same. Our sample mean, average weight of our product, or average score of participants. But for the Z, that mu was population mean. Again, if it was IQ, that would be 100. But here, mu is not population mean. It's the number that we're comparing with. For example, for the laptop, that mu will be 2 pound, 2. And for the Dorito will be 16, it's a 16 ounce. So the difference between those goes in a numerator, and denominator back to the z-score is sigma m, standard error. Again, for the t-test, it's a sm. It's the same thing, a standard error, but we read it estimated standard error. Some people don't even say estimated standard error, but that's what it is. The left z is standard error, but that's estimated standard error. But they both are standard error. So you may say estimated standard error is standard error. And you notice that for the Z was sigma M. Sigma is the standard deviation. We need to know standard deviation for all variance for the population. But for the t-test, we don't need that population. We don't have it. We need to use our own standard deviation. Our own means from the sample. If you look at the top right side of the screen, from the previous session, this is how you calculate your standard deviation and variance. S for the sample. S square variance for sample was SS over DF. At this point, you're not going to calculate the SS manually. I give you the SS, and then I ask you to calculate the variance. So SS goes on top, and DF is just n minus 1. Take away 1 from your sample and gives you DF. And S is just the square root of that. So if your variance is 9, your S, standard deviation, square root of 9 is 3. So back to our formula, it's the same thing. For the standard error, 2 ways to calculate it. And it's all you do. And instead of the standard deviation of population, sigma, lowercase sigma, you use S, which means the standard deviation for the for the sample. So you calculate the S and you put it in that formula, or you calculate the variance S squared and put it in the next one, which is square root of S squared divided by N. N is sample size. And that gives you the value for a standard error, or estimated standard error. The Cohen's d is pretty much just like the Cohen's d for the z-score. As you can see in green color, for the z was m minus mu divided by standard deviation of population, or sigma. For t is pretty much the same, except we have S, a standard deviation for the sample. DF is the same, n minus 1, and from this point on, for hypothesis, for t-test, we use Cohen's d and R square. They both really do the same. They tell us about how accurate we are. Cohen's d, for example, is the difference between the two groups, or sample and the one we compare it. The larger the difference, the better. The more power, but better means the more power your research has to reject the null. R square, let me make this larger. So R square uh, is T square over T square plus df. So you need to calculate the T, that calculated T, not the critical value for the T on page 702. As you can see on top right of the screen, in green it says CV, critical values, page 702 for the T. Once you calculate the T, the value of T, it goes, you square it. If it's 3, then it's 9. T squared is 9, and you put it on the bottom, 9, plus df. If you got 9 people, is 8. What is R square? R square is percentage of variance accounted for by the treatment, similar to Cohen's d. So this means that so first of all, once you calculate R square, which is going to be less than 1, as you can see the formula, look at the formula, the denominator is larger because the denominator is T squared plus df. It's going to be less than 1. You have to multiply it by 100 to give you percentage or probability. Let's say if it's a 0.1, so would be 10%. Okay, let's say if it's 0.6, it would be 60%. So what does that mean? It tells us that, yes, we reject the null and there are significant differences, but only 60%. That means the other 40%, there are other factors that affect our research that we did not calculate. So in other words, the higher the R square, the higher the Cohen's d, the better. And there are tables in your book. We went over the Cohen's d table, and we're going to go over them again here in a minute. And this is all the formula we just explained. And then again, we talked about this last time, one tail, right? And then two tail, that's his hypothesis. This is called inferential statistics. Infer means draw a conclusion from your sample. We use this t-test to test our hypothesis about unknown population. Unknown, that means we don't know the mean, standard deviation, and variance. It's not like they use in a standardized test like GRE, ACT, SAT, and all that. We estimate by using standard deviation or variance. Example, does this year class know more about statistic than last year? If I want to conduct this research with my students, okay, that's my research question. So I have a midterm mean for the last year class. It was 85, midterm or the final, it doesn't matter. Their average was 85, okay. The mean for this year of the class, let's say your class, is 88, okay? So we don't know what the average statistics score should be for the population. Each semester is different. 88, 85, 89, 90, 95, you name it. That's why we're using the t-test. We only compare this year's score with the last year's score. Sample data can only be considered as estimates of a population value. So again, this is just like what we did with the z-score. You need to look on page 702. I highlighted and know whether you're using one tail or two tail, directional or non-directional. The the alpha that we use for social sciences is either 0.05 or zero point zero 0.01. But here you see right there at the bottom, the blue color, 0.05, 0.025, zero point zero 0.01. We don't use those except we use 0.01 or 0.05. And they are in page 702. So you go there with your one tail or two tail test, which is specified in your uh, research question or the problem you're sort of solving. One thing you need to know, if it's not specified in the problem or the research question you're conducting, if it's not specified, you use alpha of 0.05. SPSS by default has alpha of 0.05. Also, if it's not specified one tail or two tail, always use two tail. Two tail tests are better, meaning they are more accurate than one tail tests. Again, back from the previous slides, how to calculate them, how to calculate D. I showed you that uh, the slide has all of these formula. Here's the table for effect size. We already talked about it last time. And you can see if the D, the difference between the two mean are, or two numbers are less than 0.2, there's no effect. Okay? It's not that they are the same. Null is right. That's what it means. If it's zero point 0.2 but less than 0.5 is a small effect. If it's 0.5 but less than 0.8 is medium effect. But if it's 0.8 or higher is a large effect. For R square, same thing. For t-test, we use R square, but then again for other tested statistic, we use, for example, omega square, which is pretty much the same. And we talk about that when we get there. That's the R score. R score also has table. If it's less than 0.01, it's a small effect. If it's 0.01 but less than 0.09, it's medium effect. If it's 0.09, that's a small effect. If it's less than 0.09, 0.01 is a small effect. If it's less than 0.25 up to 0.09, 0.09 but less than 0.25 is medium effect. If it's 0.25 or larger, is large effect. The larger, the better. You can report that in your research, both of them. So let's go over our research question. And once you've done that, you get a good picture of what's going on. It says the supervisor has prepared an optimism test that is administered yearly to factory employees. The test measures how each employee feels about its future. The higher the score, the more optimistic the employee. Last year, employees had a mean score of 15. A sample of 9. Keep in mind that this is just artificial, we use 9. We shouldn't have less than 30, but again, we use 9 to simplify the calculation. But in reality, if you had only 9 participants, you should just use sign test, which is non-parametric test equal to single sample t-test. But again, that's just to show you it doesn't matter how many number, how we do the calculation. So we have a sample of 9 employees from this year selected and tested. And here their score, each person score on that optimism test. One person scores 7, then 12, 11, 15, 7, 8, 15, 9, and 6. The mean is calculated for you, the mean for our sample. S is already given to you, 94. So based on this sample, can the supervisor conclude that this year employee have a different level of optimism? You see the language? With that, meaning that's non-directional. It doesn't say this year employee have a higher level of optimism or lower level of optimism. If it was higher level, then you use one-tail hypothesis or directional. You're directing, you're saying higher. I think this year employees are more optimistic or less. But it says this year is different than, okay? So with that is two-tail hypothesis. And then it tells you the alpha is 0.05. If it doesn't say, use 0.05. But it clearly stated that use 0.05. So note that this hypothesis test will use t-statistics because population mean, variance, standard deviation are unknown. We have to use our sample to estimate them. Set the level of significance 0.05 for two-tail. And here they are. We follow our hypothesis testing. Step 1, Noel says, hey, the last year mean for our employees was 15. This year, it's going to be the same. Even Steven, no difference. Zaps, 0. Nada. But H1, which is us, the researcher, we're saying, I don't think so. The mean is not going to be 15. Again, we might say the mean is going to be greater than 15 or equal, or we would say like greater than 15 or less than 15. But we're saying it's not going to be 15. That's the response to it. If Noel says it's going to be, if we say less, Noel says greater or equal. If we say more higher, it's going to be greater than, okay, if you say less, notice she says it's going to be equal or greater, opposite exactly of what we're saying. If we're saying it's going to be 15, if Noel's saying 15, so we're saying this year is not going to be 15. So that's two-tail. Step 2 is find the critical value. We need two things. We need to know if this is one-tail, two-tail. We decided it's two-tail. And then we need to know the DF. DF is n-1. N is 9. We have 9 participants. -1 is 8. With that in mind, we go to page 702. And where it says the first column, DF, is 8. And then we use, it says two-tail right there. And you go down. Let me make this large. slideshow. All right. So you see two rows. The first row is for one tail. The second row is for two tail. I circle them. And you can tell by those highlighted tails. Our degrees of freedom is 8. And then we concentrate on the two tail. Right there, when I circle the two tail, underneath alpha is 0.05. That's what we want. And you move from the 8, which is DF, all the way. I also underline it in red. So your critical value for T, alpha being 0.05, two tail, is 3.306. So step 2, find your critical value. We did 3.3. Step 3, calculate the T using that formula. And that's what we're going to do. All right, once again, if you look at your, let me make this large. On the center right side of the screen, you see the steps in hypothesis testing. Null says mean is 15. H1, alternative hypothesis says no, it's not going to be 15. Okay, so step 2, find the critical value. We did, look in, okay, page 702, critical value, and it says 2.3 right there, 2.306, right? Critical value, 2.306. Step 3, calculate the T. That's what we're going to do, and then make a comparison. If the calculated T falls into a critical region or rejection zone, then we reject. If falls short, we retain the node, or we fail to reject the node. So this is our distribution on the bottom right side of the screen. Once again, T distribution is just like Z distribution. On the bottom left side of the screen, to just remind you, that was Z. And the T is the same. You have a mean of 0, a standard deviation of 1, positive to right, positive left. So we're going to use the one on the right, which is t-test. And where is the critical value? 2.3. All right, one, you can see that if it's positive, it's two tail. So you have to cover both tails, or non-directional. If it's positive, if our calculated T turn out to be positive, we're on the right tail. And right tail, the critical region or rejection zone start with 2.306. On same token, on the left will be negative 2.306 because it's symmetrical, bell shape, but it's negative, and we have to cover both tails. Negative 2.306. All right, so that's your step 2. Let's go for t-test. In the middle of your screen, m minus mu divided by estimated standard error. M this year sample is 10 and 15. It was last year, which consider mean. Substitute the population mean. So 10 minus 15 is negative 5. That tells you we're going to fall into negative tail. And then now we need to know what is estimated standard error. Two ways at the bottom to calculate it. You can either use a standard deviation or variance on the top right side of the screen. Either way, if you decided to use the variance, which is SS over DF, I gave you the SS is 94, DF is 8, 9 minus 1. and that gives you the variance of 11.75. Then you use the bottom one when it has a square root of s squared. A square of 11.75 is 3.43. That gives you standard deviation. So you put the right one, the top one. Either way, you can see that pink circle. Your estimated standard error should be 1.14. Either way, if you use the standard deviation or variance, you plug it in right there where it belongs in denominator of t-test formula. Negative 5 divided by 1.14 is negative 4.38. That's your calculated t. And we calculate the t. Negative, we're on a negative side. So step 4, make a decision. And look at that distribution, and we know that rejection zone started with negative 2.3. So negative 4 is right there, the red dot. That red dot, bottom right side of computer, negative 4.38, that's where it belongs, which is deep into rejection zone. And what is our decision? Reject the null. So back to our problem, the problem was, is there a significant difference between this year employees' optimism regarding their jobs? Yes. Null says no. It's the same. We say no, that has a statistical significance. We reject the null. Yes, this year seems to be more optimistic. It doesn't matter, positive or negative. So again, it's on a negative side. So there is a difference. We wanted to know if there's difference. Yes, there is difference. No says there's no difference, but there are differences. On the same token, how do you calculate Cohen's d and r square? As you can see, we have the m minus mu value, 10 minus 15. S is calculated, the square root of s squared, 3.43. So negative 5 divided by 3.4 is negative 1.45. It doesn't matter, positive or negative. That number is greater than 0.8. So it has it's a big differences. It's greater than 0.8, negative or positive. So that's differences. Degrees of freedom is 8. R squared. So once we calculate the t is negative 4.38. You square it, put it on top, you put it on top, you put it on bottom, plus df, which is 8. And you square that, would be 19.18, okay? On top, that would be 19.18 plus 8, the 27.15. Keep in mind, r squared is always less than 1, but you have to multiply it by 100. So 0.70 times 100 is 70%. What does that mean? Again, this is percent of variance accounted by the treatment. It's similar to Cohen's d. It means that, yes, we reject the null based on the data that we have. 70% null is wrong. We are right. 70% we reject the null. But there are 30% that other factors contribute 30% when we don't know what they are, those 30%. So that's why the higher this R score, the better, and the higher the Cohen's d, the better. That's when you reject the null. Big difference. So that is our distribution. We're gonna Okay, so that's step 4 that we just explained. Let's do the SPSS for this, and then we do SPSS for sign test. Simply open your SPSS and variable view. Your variable are just bunch of scores that you got from that optimism test. You go to data view, so you write score. You go to data view, and then put those numbers, that 9 score that I showed you earlier for this data. And then this is the step. You click on Analyze, click on Compare Means, and then click on One Sample t-test or one sample. For the following t-test, you're going to do the same thing, identical, except instead of one sample, you click on Repeated Measure t-test, or you click on Independent t-test. But it's the same thing, really. And go to Analyze, you go to Compare Means, and then One Sample t-test. You click on it, and all these data are attached to the word right there, score. So you transfer it. It should be on this left rectangular. You have a circle. You move it from there to the right. Okay. Follow the red arrow. Put it from left to arrow. Just drag and paste it. And don't forget that the circle at the bottom, that right there, that's the score, but we don't have for t-test. We don't know what the mean population mean is, but we know the last year's score was 15. Let me make this a little larger so you can see it. So your score from here, it goes to the right. And then where it says test value, that is the score from the last year. According to your problem, research the score for the last year employees, the average for the optimism, it was 15. So put the 15 there and then click on options, and you see that um, confidence interval is 95%. And we said that 95 confidence interval is related to alpha. If it's 95%, meaning alpha is 0.05. If it's 99%, the alpha is 0.01. But that's what we want. So by default, it is 95% of 0.05. You just click on continue, click on OK. So this is your output. When you put in your data, it's called input, and then this is your output. And you can always go back and forth at the bottom because we need to go back to our input because we need to do this same thing, SPSS, but this time with non-parametric test. But let's interpret this. This is your output, and let me large it. How do we read this table? Again, if I give you this for the final and I say, what is your alpha here? Once again, you see that I circled it. It says 95% confidence interval. That tells us that our alpha is 5% in metric. In proportion will be 0.05. And then if I ask you, did we reject or retain the node or fail to reject? How do we tell? Same way that we deal with z-score. You look where it says significant. Significant, SIG, S-I-G, is two-tail test. Is this one tail, two-tail? Is two-tail test or non-directional. I circle that thick red line. That number underneath of significant to tail is 0.002. That is p-value. It's called p-value. P means probability. Now, how do we tell if we reject or retain? Look what I wrote in red, and remember that, please. It's always apply the same thing, same principle. If the p-value is less than alpha, alpha is 0.05. Is p-value 0.002 is less than alpha, then we reject the no. Is it? P-value is 0.002. It is less than 0.05. Therefore, we reject the no. The same way that we did it manually. Now, again, let's do that's the formula. Let's do the non-parametric test. Once again, the non-parametric substitute for single sample t-test is called sign test. You can always read these. You have access to PowerPoint, and also there's a link that helps you. So how do we do that? Click on your input, the data you already put in there at the bottom, either left or in the bottom center of your computer. And then you will have your data that you put in, the same numbers. But again, this time we click on, we're going to conduct non-parametric tests. Again, parametric tests are better tests because they use mean, more accurate. That's the meaning of better. So we need to have the median. We need to know what's the median for these numbers, not the mean, average, but median. We know the mean was 10, but we want to know what's the median. You can calculate that. You have your numbers. You need to click on analyze, descriptive, and then frequency, and then click on top where it says as statistics. Okay. Once again, you transfer your numbers from left to right, and then on top write your median. Okay, so because whatever your median is, you're going to write it there. It's highlighted in orange. So click on a statistic, and then all we need is we just want to know what the median is. So click on median right there when you click on statistics, median. And that gives you the value for the median, which is 11. Right there, it says median. So you go back to your input and type in 11 under the median. Type in 11, 11, 11. That means the median for all these numbers is 11. Now you have two sets of data. You go to, this is how you conduct non-parametric, in this case sign test. You go to analyze, you go to non-parametric test, you go to legacy dialog, and then you click on two related samples. You do the same thing with the next t-test, two related samples. It doesn't say single sample, but two related samples. Once you do that, here you need to decide which non-parametric test you should use, and you choose sign test, sign. You just click on it. Make sure you transfer your variables from left to right by drag and paste them, or highlight them and click on that blue arrow. Will transfer them to the right. Then okay. keep in mind that for non-parametric tests, alpha is always 0.05. You can't change it. And also we use two-tail for alpha because more accurate, and non-parametrics it helps to use two-tail and alpha 0.05. So this is what we get. This is our output for non-parametric. Let me make it larger. As you can see, it says again significant, exact significant, two-tail, 0.375. Once again, we compare this p-value, that's sig, with alpha. Alpha is 0.05. If this p-value is less than, just keep this, always remember that p-value, if it's less than alpha, we reject. It's not 0.375, it's more than alpha. Alpha is 0.05. If p-value, where it says sig, less than alpha, we reject. So it's more, we fail to reject. Could be due to not having enough participants in this case. This is more accurate because again, the first one, parametric test, we shouldn't have done that using SPSS anyway. But this is, for this, it shows that the p-value is greater than alpha. If it's less, we reject. If it's greater, that means it's gonna fall outside of it. So that's our statistics. Let's do a couple of these test hypotheses. They're very simple. Like basically it says that 16. Okay, so this is what we just did. You can use that for extra point for your SPSS. And then again, this one, it says what's the estimated standard error for sample. So you pull out that slide that has the formula, all the formula. Let me just see if I can be on the same page. Because I don't want to go back and forth and look for the slide. Okay, number 5. So always look at your problem, see what they're asking you. They're asking, what is estimated standard error? Estimated standard error, again, if you look at that slide that I showed you, has all the formula. The formula for estimated standard error for this t-test, single sample t-test, is, it depends on whether you use a variance or standard deviation. So if we calculate the variance is SS over N, or DF, SS over DF. Where is that hypothesis applied to mean? One sample t-test. Okay. And that would be 300 divided by 3, df will be 3, and that gives you 100. That's your variance. And divided by n is 4. So again, the formula is SMD, estimated standard error, square root of variance over n. So you calculate the variance, which is 300 divided by 3, the yeah, df, and then 100, and then 100 is your numerator divided by n, which is 4. 100 divided by 4 is 25. Square root of 25 is 5. So that's the answer for that one. Then on this one, a sample of selected from population, and mean is 60 again, and the treatment is administered to sample. After treatment, the sample mean is 66. So increase it. With sample variance, or based on this information, the size, so they want effect size, D. So the Cohen's D, you got to go for it, is MD. Oh, sorry. This is, hold on one second. Let me, there is. Right. Pull out the right formula for you. All right. So the Cohen's D is just like t-test, and it's m minus mu divided by s. That's the formula, m minus mu. So the different, again, you have extra stuff here. M minus mu, that means 66, minus 60 is 6, will be your numerator. I wrote it down right there, 6, divided by m minus mu divided by s. And you have s. You have variance, which is 100. So S is the standard deviation, which is square root of 100, which is 10. So 6 divided by 10 is 0.6. And that, again, you can even tell that that D is a medium effect because it's less than 0.8 and is greater than 0.5. If you don't understand what I'm saying, review this whole presentation again. And this one, it says a sample of 200. These are sample questions, just like the one that you will have in your next quiz and also for your final. So if you understand them, you're good. So this one, it says, this is, you got to pay attention. It says sample of N25, okay? So we got 25 participants. T statistic, so the T statistic is negative 2.6. If the researcher is using two-tail test alpha 0.05, the correct statistical decision is what? Well, you need to go back to page 702, find out what's the value, what's the critical value of the T. And you need two things, one tail or two tail, alpha and the DF. Well, it's easy to find out what DF is. DF is n minus 1, n is 25, minus 1 is 24. So you look, first column, 24, and then it says 25 for the statistic, if the research is using two-tail. So it's two-tail, and then alpha 0.05. If you look the same way I showed you, and you go to the F of 24, and then go to alpha, 0.05, and you will see will be 2.64. So keep in mind the critical, the T is 2.60. So your critical region start with 2.64, okay? So that means you fall short of, what is it? Oh, it's negative, okay. Means you're there. Okay, that red dot, 2.64, that means you are in the rejection. 2. Um, okay. Let's just look it up, see what is the value, okay? 2.05 to tail alpha 24. We go there, right there. Make it full screen. The F is 24 right there. And then alpha right there. You see that red light? You go down all the way. Let me see if I can see that page. 24, 24. I have, yes, 2.064. Oh, I see, 2.064. You can see it. 2.064. Let me just highlight it for you so you can see it too. Right. Oh, 2.064. 2.0 right there. 2.064 right there. So 2.064. Let's go back to it. Two point oh. Okay. It's 2.064. So let me fix this. 2.60. So 2.064. So our critical region starts with positive negative 2.064 plus or minus. But the fact that our calculated T is negative 2.6 is on negative side, and 2.6 is outside of 2.06. And that's what this is right there, 2.6. And that's what this is. is outside this critical region, or in it is a critical region start with 2.6, okay? So it falls greater because, again, the greater is like this. Maybe I should use different color. Hold on. So you can see it is inside, right? The critical region goes to 2.6. Hold on a second. Okay, 2. It starts with 2.06, but our calculated T is greater. That means it goes further than 2.06. Okay. All right, so that's for that. And then again, this one, the number for sample of 15, what t-value determined the two-tailed test? It's the same thing. You got to go, and n is 15, df is 14, alpha is 0.05, two-tail. It says, what's the critical value for the t? Just look it up like I just showed you. Okay. So next time, related or repeated sample t-test. Make sure you do your SPSS and take your next quiz on this single sample t-test. And have a good evening. Let me know if you have any question, concern. Email me. That's the best way to communicate, and I would respond to you. Good luck with all your classes. And next time, we're not going to meet next week, but after that, we're going to continue with this chapter, which will be another t-test. Again, here's all the three tests, t-tests. We cover single sample t-test. Next time, we're going to cover related, and then we'll be done with this chapter. And then next PowerPoint will cover the two independent sample. And then after that, we go for ANOVA. All right, you guys have a great evening. Thank you. And I'll see you next time. Two.